Okay, in this last video, what we're really going to be doing is we're going to be going through a couple of more involved problems. And all throughout this class, I've been saying that's an issue that you'll understand better when we get to Chapter 8. So we're going to rectify all of those issues from the past in this video as well. Okay, so the first one is a multi-step synthesis problem. How would you convert that alkene into that nitrile shown there? Okay, so if you look at this problem, it's got a cyanide group in it. And if you think all throughout this class, how many reactions have we seen that introduce a cyanide group? There's only one. That's the SN2 reaction of an alkyl halide or a tosylate with sodium cyanide. So, the immediate precursor to this has to be this halide right here. X could be chlorine, bromine, iodine, or tosylate. I'm going to choose tosylate because if we think about the structure of our starting material, we know that the tosylate is going to come from an alcohol, and we can put an alcohol on the end fairly easily, whereas it's a little bit harder to put a halogen on the end. We learned one reaction, HBr and peroxides, but that's really a hard reaction to do. Okay. All right, so the immediate precursor, if this is a tosylate, is this alcohol here. This alcohol could also be transformed readily into a bromide or a chloride through either of these two reagents, PBr3 or SOCl2. And of course, in the previous chapter, this is one of the basic reactions. How do you do the anti-Markovnikov addition of taking a alkene and adding an water across it in an anti-Markovnikov fashion? And this is, of course, the boron reagent. Okay, so this transformation could readily be done in 3 steps using this sequence of reactions right here. Again, I tried to emphasize this in the previous chapter, but the best way to do these multi-step synthesis problems is to think backwards. Look at the starting material, look at the final product and say, what could I make this from? And then all along be thinking about how any of those intermediate compounds could be made from the starting material. Okay, let's do another one. This also takes 3 steps. How could we do this? Okay, the only reaction we know that makes a nitrile is from an alkyl halide doing an SN2 reaction, but we also know that we can't do the SN2 reaction at sp2 carbon. So thus, in this one, making the nitrile or introducing the cyanide cannot be the last step of the reaction because it would require an illegal SN2 substrate. So what I'm saying here is that this would not work, right? Because we have this limitation on the SN2 reaction. Okay, so we're going to have to actually introduce the alkene as our last step. And the alkene is going to come from an elimination reaction, either dehydration or dehydrohalogenation. Turns out either of those can work. Okay, we can take either this halide and eliminate it with KOH ethanol. Since it's a secondary halide, it's probably going to prefer the elimination with a strong base. We could also do the elimination with sulfuric acid, okay? And it'll go to this side over the other side. Yeah, that's a more advanced concept that we'll get to in Chapter 10, but it would much prefer to have the pi system alignment between the alkene and the nitrile that you see there. That's something we'll discuss in the future. Okay, all right, how do we make these two compounds? Well, now cyanide is attached to sp3 carbon, right? Okay, so the immediate precursor that we need here is, of course, the halide, or the hydroxyhalide. And you'll notice that both of these are compounds that, again, in the previous chapter, we showed how you could convert alkenes into either halohydrins like this with this regiochemistry, or you can convert them into 1,2-dihalides. In this latter, there's a selectivity issue, but when you look at this, this is primary, this is secondary, so this halide here should be better in the SN2 reaction. Okay, and of course, these are compounds that you could get in one step from the designated starting material, vinyl cyclohexane or ethynyl cyclohexane, whatever you want to call that. Okay, all right, so let's look at a roadmap problem here. Suggest a structure that corresponds to letters A, B, C, and D. Okay, the beauty of a roadmap problem is that you can start from either end, and that can help you find the structures in the middle. Let's just look at the final products. We know that, let's just call this one E and this one F. The last step of this reaction is very obviously an SN2 reaction, right? And so that means that E is going to come from something like that, and F has to come from something like this, okay? And this we know because the SN2 reaction goes with inversion of configuration. As far as what is X, is it a halide or a tosylate, you can sort of get a clue that X is going to be a tosylate by the reaction that's producing B and C. Okay? All right, so B is probably going to be an alcohol, and C is going to be a tosylate. Okay, so somehow or another we have to get an alcohol into this. Let's just look at this roadmap going forward. First step, we're treating a tertiary halide with a strong base, a strong oxygen base. We know that this is going to produce the E2 product and not the SN2 product. So this is going to cause an elimination. Okay, our product started out, I guess, actually it's not a chiral compound, is it? No, it's not. Okay, but we're just looking at the relative stereochemistry here. Okay, so this is the product of this reaction right here. Okay? All right, in step 2, we're going to add water in an anti-Markovnikov fashion. This is the combination reagent that does that, right? So this is anti-Markovnikov addition of water. Okay. All right, so it's also going to come from the side opposite the methyl group. Okay, so remember that hydrogen and OH both add to the same face of the molecule. So both of them are going to add from the face that's opposite the methyl group. B is going to be the compound shown here. All right, tosylate is going to be made from the alcohol, and there's no change in the configuration of the OH group because this is a reaction that's making the OS bond. So nothing is happening to the CO bond, right? So we're making the bond between O and TS. Okay? All right. The SN2 reaction here is, of course, going to go with inversion of configuration, and that's going to produce the sulfide with the opposite configuration. Here, even though it's secondary, the SN2 is favored because the sulfide is a better nucleophile and a weaker base than the alkoxide. Okay. Reaction with sodium iodide is also going to occur with inversion of configuration. That is also an SN2 reaction. We have to be careful with the conditions here because the iodide that we make in this could also do an SN2 reaction again, and this would just scramble our stereochemistry. All right, so in the last step, we're treating it with the allyl sulfide compound, and this is producing the final product, again, with inversion of configuration. Okay, so we're also getting inversion of configuration. Okay, let's look at some SN1 and SN2 issues from the past. Let's see, in chapter 4, we looked at quite detailed at this reaction between alcohols and HX compounds to produce the alkyl halides. Okay, so with a secondary and tertiary, it went through what we call the SN1 mechanism, where we make a carbocation, and then the halogen comes in later and produces the product. So this part of the reaction here is really just the SN1 reaction, right? It's exactly like the SN1. We dissociate, make a carbocation, and then substitute in the last step. Okay? When it's a primary or methyl halide, it goes by an SN2 mechanism. And the reaction is far more efficient with HI than with any other halide. Okay? So now we can understand this. Okay? The primary halide, like we have here, is the best type of halide for an SN2 reaction. And the iodide is the most nucleophilic of the halogens. So it's much better in the SN2 reaction than the chloride or the bromide. So this now explains those issues. Okay. What about this reaction from chapter 6, bromination? We said that we're going to, sorry, I forgot to turn the email sign off. Okay. All right. So we're going to get the trans isomer, and we're going to get it as a 1-to-1 mixture of enantiomers. Okay? All right. So remember we said it's questionable whether you ever make this, but once we get here, this is, of course, a symmetrical compound. This has no optical activity, right? There's a plane of symmetry right where I'm moving the cursor, so it's thus an achiral meso compound. Bromine can attack either face and attacks anti to this bromine because this again is an SN2 type displacement. It can attack either one, attack from what I'll call the B carbon, or from the B direction gives B. Okay, so this is B attacking this carbon right here to give this compound, which if you just turn it around on the z-axis. I can't draw a good z-axis here, but if you just turn it around, you'll see that that's B. And attacking the other carbon gives A, and there's an equal likelihood of attacking either other carbon in a non-chiral environment. Thus, we get the enantiomeric mixture. Okay, What about SOCl2 and PBr3? Well, what they do is something kind of similar to what we're doing with tosylates. So SOCl2 is this compound right here, okay? And what you're seeing here is that it makes kind of this compound here known as a sulfinate ester, which is a reasonably good leaving group. Chloride comes along and does an SN2-like displacement of this, making SO2, sulfur dioxide, and HCl. In PBr3, we're also converting the alcohol into a leaving group. This is now something of a leaving group. Bromide attacks in an SN2 fashion to give us the bromide, okay? And the first attack here actually produces this compound, but it still contains two PBr bonds, which can also activate an alcohol unit. Eventually, we're going to end up with phosphorus acid, this compound over on the right. Okay, and this is the final slide. I'd just like to show a feature slide here. And this is the commercial synthesis of the anti-AIDS drug, AZT, from the DNA-based thymidine. Okay, and what we're seeing is that every step in here is either an SN1 or an SN2 reaction or making something like a tosylate. Okay, so in our first step, we're going to take this compound, triphenyl methyl chloride, and this compound, and a base, and what's going to happen here is this alcohol here is a little less hindered than this one, so this one's going to make the alkoxide, and that's going to do the displacement there. You're probably saying, hey, didn't you say you can't do an SN2 at a tertiary halide? Well, this really isn't a tertiary halide. We're going to learn in chapter 11 that the phenyl ring actually, or the benzene ring here, is going to activate an adjacent halogen for the SN2 reaction, and we also have no hydrogens at the beta carbon for an E2. So we can't do an E2 in this system. So the SN2 occurs, and this produces the ether that you see right here. All right, now we're going to take the other alcohol and turn it into a leaving group. Instead of using the para-toluene sulfonyl chloride, we're going to use methane sulfonyl chloride. That apparently is a little bit cheaper, and so for the large industrial scale preparation, this is preferred. Okay, this is not a stable compound because an intramolecular SN2 reaction can occur. Okay, so what's going to happen is a base is going to pull this acidic proton off. Okay, it doesn't take much of a base to do that. And then an intramolecular SN2 occurs to make the bicyclic, or actually technically tricyclic compound that you see as the next step of the reaction. Sodium azide does the SN2 reaction with inversion of configuration to get the compound immediately to the right, and we just have to remove the triphenyl methyl group in an SN1-like reaction with HCl to produce the final product. I guess the byproduct in this case is triphenyl methyl chloride, and this is the actual pharmaceutical compound azithromycin, which again was the first drug approved for the treatment of AIDS. Better ones have come along since, but in the early days of AIDS, this was a drug that had a dramatic extension on people's lives. They eventually found that you'll eventually become resistant to AZT, but better drugs and drugs used in combinations have been far more effective treatments. Okay, I think this is the last slide in this video. No, sorry, one more. Okay, so we're going to just look at whenever somebody wins the Nobel Prize for organic chemistry, I like to point out, and it's a little bit deeper than this, but the Nobel Prize in 2010 was awarded to these three people here, and what they pioneered was a way to actually do the SN2 reaction at sp2 carbon. Okay, so it turns out that instead of having a sodium or lithium or potassium counterion, what you have here is a boron counterion, and this is more of a covalent bond than an ionic bond. Okay, you have to throw in some sort of palladium species, and in the presence of the palladium species, you get the successful substitution reaction. Okay, an alternative coupling is this reaction here, known as the Heck reaction. It's one of two reactions we talk about in organic chemistry that have sort of a mild cuss word as part of their term, but it's actually named after Professor Heck at Delaware. But and we'll see reaction later that has hell in its name, Hell-Volhard-Zelinsky reaction. But anyway, this is also a nice way to make carbon-carbon bonds at sp2 carbon. Okay, is through the Heck coupling. Okay, and it really doesn't involve a anion equivalent like we have in the Suzuki reaction, which is the reaction at the top. Okay, what did Negishi do? Okay, in Negishi's case, we have zinc as the counterion that does the reaction. Turns out that boron's probably the more convenient one because it's stable with respect to water, and it's kind of revolutionized drug design. Okay, basically, you can couple almost anything, or you can couple almost any two carbons now because of the invention of this reaction.